Bismillahirrahmanirrahim. So, hello everyone. So today we will solve a recitation problem for chapter 24, which is about electric potential. Okay, let's start by the first problem, which reads, an infinite line of charge has uniform linear charge density. So I give you the uniform linear charge density, lambda. Okay. So this is the infinite line. It has a uniform linear charge density lambda, which is equal to 10 to the power minus 8 coulomb per meter. So a point A is at a distance of 2 meters from the line. So let's say point A is here. And this distance here is 2 meters. And point B is at a distance of 3 meters from the line. Let's say point B is here. And the distance between the line and point B is RB, which is 3 meters. What is the magnitude of the potential difference between point A and point B? Okay. So they want the magnitude of the potential difference. So basically VB minus VA, but we want the absolute value or the magnitude. So how do we get this? Well, you know that I can get the differential of potential, the potential difference, V final minus V initial between 2 points is just minus integral between initial and final of E dot ds. Okay. So if I know the electric field created, and then I know ds, which is a vector displacement, I can know what the potential difference between initial and final. So here, let me apply it, between A and B. So I want VB minus VA is just minus integral. You see initial, so meaning A. So I start from A and I go to B of E dot ds. So what is ds? ds is just, let me take another color. So I'm going now from A to B. So A is here, B is here, of course. ds is in this direction. Okay. So actually ds here is equal to dr. Now let's assume that, of course, here it's positively charged. I can choose negatively charged also. That's why I'm asking you absolute value. Whether it's positively charged with this linear charge density or negatively charged, it doesn't really matter if I take the absolute value. So if it's positively charged, the electric field is pointing away. Okay. So E dot ds, so this is just minus integral between RA and RB. Now E dot ds, you see that E and ds are in the same direction. Yeah. So it will be just E multiplied by ds. By the way, ds here is equal to dr. Okay, because the angle between them is 0 degree. Yeah. Now what is this E? Well, I know E. So E is just, so this is an electric field created by a line of charge, an infinite line of charge. So it will be lambda divided by 2 pi epsilon naught r. And we demonstrated this using Gauss law. And of course, you can also write it like 2k lambda divided by r. Okay. So I will have here minus integral between 2 meters and 3 meters of 2k lambda divided by r dr. So the constant, I get it out. I will have minus 2k lambda. Now what is integral of dr divided by r? So this is len of r. But I will have len of r, but I will take it between 2 and 3. And this will just give me minus 2k lambda len of 3 divided by 2. Okay, so I know everything here. Okay, so minus 2, k is 9, 10 to the power 9 SI units. Lambda is already in SI units, so it's just 2, 10 to the power minus 3. And then I take len of 3 divided by 2, and you do it. how much do you get? You get VB minus VA is just minus 146 volt, but I want the absolute value, so I'll have plus. Okay, so A is the right answer. Okay, and you see here that VB, if this is positively charged, of course, you know, VB will be lower, smaller than VA. So VB, that's why basically here it's negative. This is VB minus VA. Okay. If it was negatively charged, the E will be pointing towards A, towards a line. So you will see that VB minus VA will be positive. That's why I'm just talking about absolute value, magnitude of the potential difference. So they get rid of the minus sign. Okay, good. And the solution is given again, and you can have a look at it. Next problem. Okay, let me erase the board. So have the good habit before you solve any problem, have the good habit of going through the slides and remember what we did in class, and you know, you take your notes and you study the important, you write the important equation and you understand them before you start the recitation. Now in problem number 2, we have in a certain region of space, the electric potential is given by this. So I have V, which depend on X, Y, and Z, and V is just minus 2 X, Y, Z square. So V is in volt and X, Y, and Z are in meters. The question is very simple. Find the magnitude of the electric field at a point with the vector position this. So I have a point P, and point P has XP, which is equal to 2. So that's the X coordinate of the point P. YP is equal to minus 2, and ZP is equal to plus 4. So at this point, I want to get the electric field. What is the magnitude of the electric field? That's the question. What do? You know that if I know V, so in the previous question, I know the electric field, and I want to get what is delta V. And we use a formula, V final minus V initial, just minus integral of E dot ds. If I know the electric field, I can know what's the change, what the potential difference between 2 points. Now here is the other way around. I know the electric potential. I want to know what's the electric field. Of course, you know that the electric field has 3 components. The first component is minus derivative of the electric potential with respect to X. It's a partial derivative, of course, minus partial derivative of V with respect to Y, minus partial derivative of V with respect to Z. And this is what we did in class, okay? If I know V, I can know what is EX. So this is EX, of course. This is EY, and this is EZ. And we already demonstrated this in class. So let's take the derivative now of this minus, of course, here we'll have plus. So EX will be just minus derivative of this formula, this V with respect to X. So of course, Y and Z are constant. You know how to take the partial derivative. So you know this in math, so I will not spend much time. So minus minus will give me plus. If this X is constant, I just have to YZ square. This is my EX. Along EY here, along Y, I take minus partial derivative of V with respect to Y, and then I just get plus 2X Z square. And EZ will be what? So now I derive with respect to Z, X and Y are constant, so I'll have minus 4. But minus minus will give me plus, so 4xy. Now if I derive this Z square will give me 2, 2 multiplied by 2 gives me 4, of course. So here I have Z. Okay. Good. So now let's put it now this way. EX, of course, now I will be replacing, I'm looking at the electric field at point P. So I replace X, Y, and Z by 2, minus 2, and 4. If I do that, I will get here minus 64 Newton per Coulomb or volt per meter, because you remember Newton per Coulomb is also volt per meter. You see this is in volt, this is in meter, so volt per meter. EY, you get plus 64 volt per meter, and EZ, you will get just minus 64 volt per meter or Coulomb per meter. So the magnitude will be just square root of 64 square plus 64 square plus 64 square. Okay? All of them have the same magnitude, just the sign is different. And you take the square, it doesn't matter. So you calculate it and you take the square root, of course, and you get 111 volt per meter. Okay. Good. Now let's go to the next problem. So here I have point A, point PE, P1 and point P2 that are located in the XY plane. And I give you the coordinate of point P1 and the coordinate of point P2. Now, if the electric field here is constant, okay, so I have a certain coordinate of the electric field along I hat, along J hat and along K hat. So my electric field is along X, Y, and Z. It has component along these three directions, whereas my 2 points are on the XY plane. So the Z is 0. Okay. The question is very simple. Again, calculate VP1 minus VP2. So calculate the potential difference between point 1 and point 2. We know the electric field. So how do we do? We already calculated that. So we can get the potential difference, delta V, if we know the electric field, by taking the integral, minus integral between initial and final. Initial here is this P2. Don't make this mistake, okay? This is final, and this is initial. So here it should go from initial. So P2 to P1 of E dot ds. Okay? Now electric field is constant, so let me take it out. So I have minus E vector dot. Now what's the integral? What is the integral between P1, P2 and P1 of ds? Well, this just gives me the vector. This gives me which vector? The vector P2, P1. Okay. So the delta V that I want, VP1 minus VP2, is just minus E dot. So I have a dot product between the electric field and P2, P1, a vector P2, P1, because it's a displacement, okay? I'm looking for the vector displacement. I'm going from P2 and I'm going to P1. So what do we have? Of course, a dot product, we can say that this is minus. Let me put the component. Component of E is 4.34, component, along X, along Y, 13.8, and along Z, 45.6. And this dot product, P2, P1. Now, what are the coordinates of this displacement? P2, P1. What do you think? So of course, I will start by P1. Okay. So you see P1, what are the components of P1? 2.75, final minus initial, okay? 2.34 and 0 minus initial. So the coordinates of P2. So what are the coordinates of P2? 7.83, 4 points, okay, and 0 here. And then you know how to calculate this dot product. This multiplied by this, plus this multiplied by this, plus this multiplied by this, which is 0. Okay. So at the end, you will get plus 52.7 volt. Okay, this is VP1 minus VP2. Okay, this minus here, so this will be negative. Okay, but also this will be negative. So that minus and this minus will go away. Okay, you know how to calculate this, right? So it will be minus EX. P2, P1, X minus Py times P2 P1 y. This is P2 P1 x. This is P2 P1 y, and of course this is 0. Okay, that's 0. So you get it. Okay, very simple and very clear. If you solve all the recitation problem, I'm sure you'll not have any problem in the final exam. And of course, no problem in the quizzes. Okay, so this is what we did here. And of course, it gives us the right answer, 52.7 volt. Next. So what do we have here? Let's read the question very carefully. The distance between two particles, Q1 and Q2, is 1.32 centimeters. So I have Q1 here. It has a charge 3.49 microcoulomb. And then I have charge Q2 here. It has a charge 5.73 microcoulomb. And the distance between them, let me call it R initial, is 1.32 centimeters. The question is, what is the work needed to make the distance between them 2.56 centimeters? Assume that the particles are stationary at the initial and final position. Okay. So let's assume that this is initial, now final. Q1 is still here. Now Q2 moves here. Okay, Q2 is here. And the distance here between them is R final is 2.56 centimeters. Okay. So this is my initial situation, and this is my final configuration. Of course, kinetic energy initial is 0 because it's said here, and kinetic energy final is 0. Okay. The particles are static at the beginning and at the end, in initial configuration and the final configuration. So the question is, what is work applied? What is the work needed to do this? Very simple. You use conservation of energy, mechanical energy. Delta K plus delta U is equal to work applied. Okay. Of course, here delta K is 0. Kinetic energy final is 0 minus kinetic energy initial is 0. So work applied that I'm looking for is just delta U. Now, what is delta U? Well, it's U final minus U initial. So what is U final? U final is the electric potential energy linked to this configuration here. What the electric potential energy, U final, we know it. U final is just K. This is the formula, and we already talked about this in class, is Q1, Q2 divided by R final, okay? And here, what is U initial? U initial would be just K, Q1, Q2 divided by R initial. So U final minus U initial would be just K, Q1, Q2, 1 divided by R final minus 1 divided by R initial. Okay. So this is my work applied. Let's calculate it now. 9, 10 to the power 9. That's K in SI unit. Q1, you put it in SI unit, of course. So you have 3.49, 10 to the power minus 6. Q2, 5.73, 10 to the power minus 6. Now 1 over RF. What is RF? RF is 2 centimeters. You put it, of course, in meters, right? So 2.56, 10 to the power minus 2, minus 1 divided by R initial, which is 1.32, 10 to the power minus 2. You calculate. So how much do you get? If you calculate, you get minus 6.60 joule, and this is the work applied. Okay. Now, why this is negative? Why the work applied is negative? Well, that makes sense. Yeah. Because look here, these two particles are both positively charged, so they repel each other. Okay. So you remember that basically this work applied is just delta U. But remember, what's delta U? Delta U, which is the change in electric potential energy, is just minus the work done by the electrostatic force. Okay. Minus the work done by the electric force. Okay. So if work applied is negative, that means that the work done by the electric force is positive, and it's equal to plus 6.6 joule. Well, this makes sense because the work done by the electric force, wants them to be far away from each other. Okay. So here you see the displacement is this. This is the displacement. Okay. In this direction, delta R. Okay. And the work done by the electrostatic force is in the same direction. So the work that I'm doing is opposite to the displacement. That's why it's negative. So basically, the work applied, the work needed is negative here. But the work done by the electric force is positive because it's in the same direction as the displacement. They want to repel each other. They want to be far away from each other. Okay? So I have to, apply an opposite force basically to control it. So the work applied should be negative. The work done by the electric force is positive. I hope it's clear, and this you know it already from Physics 101. I'm just discussing that. So let's go to the next problem, which is this. Consider a spherical shell of radius r of 10 centimeters. And this spherical shell has a charge Q1, which is minus 20 microcoulomb. So let me just draw that. Okay. So I have a spherical shell. Let's say this is my sphere. It has a radius r, capital R, which is 10 centimeters. Of course, I should put it in meters when I calculate SI units. And the charge all around, uniformly distributed, is Q1, which is minus 20 microcoulomb. Okay. Next. So let me change color here. A point charge now that has, so Q2 here is here, and is equal to plus 40 microcoulomb is located at the center of the shell, okay, the center. So the question is very simple. Calculate the electric potential inside the spherical shell when R1 is equal to 8 centimeters and outside when R2 is equal to 20 centimeters from the center. So I want the electric field here at R1, and R1 is equal to 8 centimeters inside, and the electric field outside when R is equal to 20 centimeters. So R2 is 20 centimeters. Okay. I want the electric field. No, sorry, it's the electric potential. I want the electric potential. We will get also the electric field. Okay, let's start by outside. When R is bigger than the radius, what is the electric potential outside? So now the electric potential V outside, both will contribute. Okay, I have my spherical shell here, which is negatively charged. It will contribute to this potential here. And how does it contribute? Well, you know that it will contribute like a point charge located at the middle. So I will have contribution V from the shell plus contribution from the point charge. What is the contribution from the shell in the electric potential? Well, it will behave like a point charge. So it will be K Q1 divided by R2, and R2 being the distance between the center and where I'm looking, where I want to calculate the electric potential. Now, what should be V2? Well, V2 is very simple. It will be just K Q2 divided by R2. Okay. Now let's calculate this. If you calculate this, it will give you K, which is a common factor, basically 10 to the power 9. Q1, I know Q1, it's minus 20. I put it in Coulomb, of course, right? So 10 to the power minus 6 Coulomb. And then I divide by R1, R2. What is R2? 20 centimeters. So 20 centimeters is 0.2 meters. Plus Q2, what is Q2? It's 40. And of course, I divide by the same distance, okay? 40, 10 to the power minus 6, divided by the same distance, okay? Which is 0.2. And you can calculate that. So outside, the electric potential is equal to what? In my calculation, well, of course, this is just K Q1 plus Q2, basically, which is Q net, divided by R2. This gave me 4.5, 10 to the power 6 voltmeter, or Newton per Coulomb, if you prefer, okay? And this is the electric potential at this distance here, okay? V2 is just, V at this distance, okay? At 20 centimeters is just 4.5 million volt. Yes, volt, not volt per meter, sorry. Of course, the unit is just volt, okay? Because I'm looking for the electric potential, okay? So 4.5 10 to the power 6 volt, okay? Now, what about inside? Inside is very simple as well. So I want, when R is smaller than the radius, what is the potential inside, electric potential? The electric potential inside V1, V will be also V1 plus V2. Now, what is the electric potential from the shell? You see the shell inside, you will have a constant, because actually the electric field inside is 0. Electric field inside is 0, meaning what? I mean, due to the shell, I'm talking due to the Q1, okay? Means that the V created by the shell is constant, okay? So what is the V created by the shell alone? Okay. V created by the shell alone will be just K Q1 divided by the radius of the shell. And we already demonstrated this in class, okay? And it's a constant. That's why the electric field created by the shell inside the shell is 0. Okay? Gauss law, only by the shell. So this V1 is just K Q1 divided by the radius of the shell. And we demonstrated this in class, okay? It's just this V1, but I take R equal to the radius, okay? Because I want continuity. And then V2, that's also it's a point charge, it's just K Q2 divided by, now the distance between the charge and the point I'm looking at, which is R1. So we can calculate this, we know everything here. We know K, 9, 10 to the power 9. We know Q1. So what's Q1? Minus 20, 10 to the power minus 6, divided by the radius is 0.1, plus Q2, what is Q2? 40. You put it in Coulomb, and you divide by the distance, okay? The distance here is 0.08. And you calculate this. If you calculate this, how much do you get? You get 2.7 million volt. Yeah. So let me summarize here. So this is what I get. Okay, I will come back to this, but this is extremely important. Okay. Okay. If I have a shell outside, shell which has a charge Q, okay, outside the electric potential outside is just KQ divided by R, like a point charge. But inside, the voltage, or let's say the electric potential, will be just K q divided by the radius of my spherical shell, which is a constant. Okay? And if I just plot v as a function of the radius, so I have, this is as a function of the distance r, this is the radius of my shell inside. So I have two regimes. This is when r is smaller than r, this is inside basically. When r is larger than r, this is outside the shell. So when I'm inside, the potential is constant, and when I'm outside, it's decreasing as a point charge. So here I just have potential, which is kq divided by r, and here I have potential inside, which is just kq divided by the radius r, and it's constant. Okay, it's constant here. And we did this in class, so remember that this is extremely important. Okay. What about the electric field? Well, electric field inside will be 0 due to the shell. Okay, so the electric field inside is 0. Now the electric field outside will be like a point charge, kq divided by r squared. This is E. But E inside will be 0. That's why the potential is constant inside. And you see the potential is continuous. Okay, that's why here I'm just taking the value of the potential here at the radius. Okay, and I have a continuous potential. Go look at the lectures as I define your notes basically. I already did that in class. Okay, radius. So this is what we did here. Exactly, this is what I told you. Okay, this is inside, it's constant, v q1 divided by r, and inside, of course, due to this charged particle, it's just this distance r1. Okay, v q2 divided by r1, and you got it. Outside, both of them behave like point charge, 2-point charge. So v at r2 is just k q1 plus q2 divided by r2, and this is what we did here, and you get it. Okay, great. Yes. Next. So now let's solve this problem here, which is just as the problem we solved before. So we have a metallic sphere that has a charge of 13.5 nanocoulomb and a potential of 79.5 volt, right? And the question is very simple. 79.3 volt. But what is the diameter of the sphere? Again, we have a metallic sphere. This is a metallic sphere. Outside, I know. So the metallic sphere here has a charge Q, and Q is 13.5 nanocoulomb. What is the electric potential outside? Easy, like a point charge, K Q divided by the distance between where I'm looking and the center. Okay, this is outside when R is bigger than the radius. Okay. Now, what about inside, including the surface? Inside, including the surface, I have an equipotential. The V is constant. And as we said before, the V of a metallic shell, the electric potential of a metallic shell is constant. Okay. A metallic shell constitutes an equipotential. Okay. So V is constant. V at the surface and V inside is constant, and it's equal to what? K Q divided by R. This is what I said before. Okay, if I plot V as a function of the distance R, I look at two regimes: inside when R is smaller than R, and outside when R, the distance is bigger than capital R, and here it's constant. Okay, and it's equal to K Q divided by the radius, and from here just decay as KQ divided by the distance R. Okay, so here is distance dependent outside, but inside is constant, and it just depends on this. Okay, so the potential that I gave you, V, which is 79.3 volts, this is just K multiplied by the charge Q divided by the radius R. So that means I know the radius. What's the radius? Radius will be K, which is 9, 10 to the power 9, multiplied by Q. What is Q? 13.5 nanocoulomb. So we put it in coulomb, 10 to the power minus 9, and you divide by the voltage. What's the voltage? 79.3. So let's do this calculation. If you do the calculation, you find a radius of what? A radius of 1.53 meters. That means what's the diameter? 2 times the radius, so 3.06 meters. Okay, I hope it's clear. Good. And exactly that's what we did here. Okay, so you need to know this. Okay, as we discussed already in class. Now, question number 2. What do I have here? Well, I have a charged particle with a positive charge. This is my positive charge. Okay. Let me call it Q plus. So Q is plus 7.35 microcoulomb. So it released in an electric field. Okay. At a point A, the particle is at rest. And at point B, the particle has a kinetic energy of 1.29 microjoule. The question is, what is the electric potential difference between these 2 points A and B? Okay. So I'm talking about kinetic energy, release from rest, etc., etc. So you know that I have to use work kinetic energy theorem. Or I can use basically conservation of mechanical energy. But before that, let's draw, okay? So let's say this is my point A, and this is my point B. Okay. So at point A, I'm released from rest. So the kinetic energy here initially is 0. Let's say point B is my final kinetic energy. Kinetic energy final is given. At point B is just 1.29 microjoule. Okay, good. Now, let's assume that the electric field is constant, okay, is uniform. So the electric field is always going towards lower potential, right? Okay, so the electric field is moving towards lower potential. So you see that the electric field is in which direction, if you think? What do you think? Of course, the electric field is going in this direction. Why? Because my charge is positively charged. Okay, so Q is positive. So the force on Q will be in this direction. Okay. Okay. Good. Now, I know that if the electric field is pointing in this direction, of course, I'm pointing towards the lower potential. So basically, VA is larger than VB. That means VB minus VA. So VA should be larger than VB because electric field is pointing towards lower potential. So VB minus VA should be negative, and we will see that it's negative. But that's not the point. Let's calculate the VB minus VA. I don't want the sign, I want the value. We can use this. We can say that change in kinetic energy plus change in electric potential energy is equal to work applied. Okay. Now, what is the work applied here? I release the particle. So the particle is moving by itself. I don't exert a force on it. So it's an isolated system. So the work applied is 0. Okay. I just left it in this electric field. I release it. So it's a natural motion. There is no external agent applying a work. Okay. So we find that if work applied is 0, of course, delta E will be equal to minus change in kinetic energy. Okay. Now, what is delta U? I mean, delta U is minus the change in kinetic energy. What is delta U? What do you think? delta U, of course, is Q delta V. And we already demonstrated this in class. Do you remember this? Okay. Delta U is just Q delta V. So here I will have Q delta V is minus delta K. So that means delta V, which is VB minus VA, is minus delta K divided by Q. So it will be what? Minus delta K, K final. So I'll have minus 1.29 10 to the power minus 6 joule, minus 0 because the initial kinetic energy is 0, divided by Q, which is 7.35 10 to the power minus 6 coulomb. Minus 6 goes away, and you end up with VB minus VA is equal to minus 1.29 divided by 7.35. And this gives you, in my calculation, minus 0.176 volt. So here there is a mistake here, okay? So this 10 to the power minus 1 volt. Okay? This is what I find, okay? So, do you got it? Do you get it? Okay, good. Now, there is here a small mistake here. Yes. So V2 is 9, 10 to the power 5 volt. Okay. I think I said a mistake before. I said 4.5, 10 to the power 6 volt. No, it's 9, 10 to the power 5 volt. Okay. Good. Now, let's go to the next problem, which is very important. So in this figure, we have two conducting spheres, one having twice the diameter of the other. They are separated by a large distance compared to their diameter. So here I have one sphere. The diameter is D, so the radius is D divided by 2. And here I have a larger sphere, metallic sphere, conducting sphere. The radius is D. Initially, the smaller sphere, so initially, this is initially, the smaller sphere has a charge Q, which is 10 nanocoulomb. And the larger sphere, 2, so this is 1, this is 2, the larger sphere here, so this is Q1, okay? And Q2 is uncharged, Q2 is 0. So the larger sphere 2 is uncharged. So this is initially. Okay, now, the question is, if the spheres are then connected by a long thin conducting wire, what is the charge on each sphere? This is a very important problem, okay? Now, in the final configuration, I connect them using a wire, and the wire is long, thin, and conducting. Of course, because I connect them now, they will exchange charge, right? Now, when they exchange charge, so this is final. Now, the question is, what is Q1 final? And what is Q2 final? Okay. Is it clear? Okay. Now, let's calculate. First thing first, we will have conservation of charge. Okay. So basically Q1 plus Q2 initial will be equal to Q1 plus Q2 final, as we said before. Charge is conserved. Conserved. Okay, charge is conserved. The amount of charge in the universe is conserved. The amount of charge in two isolated systems, in an isolated system, is conserved. You can have exchange of charge, of course. So Q1 plus Q2 before and after will be just 10 nanocoulomb. So 10 nanocoulomb. Okay. If you add these two, you get 10 nanocoulomb. Okay. And that should be conserved. So I have my first equation. 10 nanocoulomb will be Q1 final plus Q2 final. Now, how do I get the second equation? Here, you see here, This is different from chapter 21. In chapter 21, I used to give you the same size conducting sphere. Okay. If they have the same size, they will just exchange and each of them will take half of the charge. So if these two spheres have the same charge, what will happen? Q final 1 will be 5, Q final 2 will be 5. Same size. But here they don't have the same size. Okay. So they will not, take the charge, let's say, equally. So what should I do? Let's take another pen here, another color. Okay. Now final, what will happen? They will exchange charge and this will have Q2 final and this one will have Q1 final. Now when will the exchange will stop? The exchange will stop when the potential here, V1, will be equal to the potential here, V2. So there will be no differential of potential anymore. So now the charge will not be transferred anymore. So after static equilibrium, we will have V1 is equal to V2 final. Okay, you got it? So this now will give me the second equation that will help me solve the problem. So V1 final, it should be equal to V2 final. So this conducting sphere will be an equipotential. And at its surface, I will have V1 final. And that V1 final, as we said before, is just KQ1 final divided by the radius. And the radius is D divided by 2. Now, what is V2 final? Of course, this is a conducting sphere as well. The potential energy, electric potential is constant also here. Okay? And it's constant, it's equal to KQ divided by the radius. So V1 is KQ divided Q1, of course, here Q2, K divided by the radius. So it will be KQ2 final divided by the radius, which is D. You see that the K will simplify, D will simplify, and I will end up with Q2 final is just what? 2 times Q1 final. Okay, good. Now I have my second equation, 2 unknown. Okay. So equation 1, equation 2, I combine them. I will find that Q1 final will be equal to 3.3 nanocoulomb and Q2 final will be equal to 6.6 nanocoulomb. If I add them, of course, I see that I have conservation of charge, 10 nanocoulomb, and you see that Q2 final is 2 times Q1 final. Okay. So what is governing this is the potential. When I connect them, the potential now will be the same. Okay, they will exchange charge such that the final charge will give you equipotential. Okay, the potential here will be equal to the potential here. Okay? And of course, these potentials are constant all over this. And I know the value. The potential inside and at the surface of a conducting sphere is just K Q, which is the charge of the sphere, divided by the radius, as we demonstrated before. And you use that and you see this. Okay, so this is a key equation here. Now let's solve a similar problem, which is this. It's the same type of problem. I have 2 metal spheres, 1 and 2. This is radius 1 and radius 2 is 2 times radius 1 as before. Now here I have charge Q1, which is 22, and charge Q2, which is minus 10 nanocoulomb. So Q1 here is equal to plus 22 nanocoulomb and Q2 is minus 10 nanocoulomb. So first thing first, this is conserved. So what's the total charge? Okay, charge, let me write it here, is conserved. So charge before Q1 plus Q2 initial, which is equal to 22 plus minus 10, which is equal to plus 12 nanocoulomb. This should be equal to Q1 final plus Q2 final. Okay, charge is conserved. 12 nanocoulomb. Okay, so initially they are far away from each other. Why I'm putting them far away from each other? Because I don't want, they interacting. I don't want them to interact. So I will not have induced charge. They don't feel each other. Then these two spheres that are separated from each other by a large distance compared to the radii will be connected by a thin wire. By a thin wire, I mean a thin, long conducting wire. Now they will be able to exchange charge. Okay. Now they will be exchanging charge. This exchange of charge will stop when? When the potential here, V1 will be equal to the potential here, V2. Okay. So the potential here, we know it already. We know also what's the potential here. So the potential inside and at the surface of a conducting sphere is just K Q divided by the radius. Okay. So final, what do I have? I will have V1 final will be equal to V2 final. Okay. Okay. They should be at the same potential, such that now there is no differential of potentials. Now the charge will not be moving anymore. So this will give me what? K Q1 final divided by the radius, which is R1. This will be equal to K Q2 final divided by the radius of the second sphere, which is R2. But R2 is 2 times R1. So K simplify, R1, R2 simplifies. So I get K2, which is K2 final, should be just 2 times K1 final. So I have my two equations. This is equation number 1. This is equation number 2. I combine them and I find that Q2 final should be equal to plus 8 nanocoulomb, and Q1 final should be equal to what? Plus 4 nanocoulomb. Okay. If they had the same size, Q1 final and Q2 final will be equal, and it will be equal to 12 divided by 2, which is 6 nanocoulomb, right? But they don't have the same size. So I have to use this equation and use this equation that we already talked about. Okay, so the larger sphere will have more charge. It will have 8, and this one will have 4. And of course, both of them respect equation 1 and equation 2. Now, that's still not the question. The question is, how much charge is lost by sphere 1 when electrostatic equilibrium is reached after connecting them by this thin, long conducting wire? So how much charge is lost by sphere 1? Well, how much charge is lost by sphere 1? You can say that it will be basically Q1 final. So the number of charge lost by it will be Q1 final minus Q1 initial. So this will give you what? Q1 final is plus 4 minus Q1 initial. What is Q1 initial? Which is 22. So this gives you minus 18 nanocoulomb. Okay, but so how much is lost? Of course, 18 is lost. So I go from basically 22 for Q1. So I started from 22 nanocoulomb, and I go to what? 4 nanocoulomb. So how much did I lose? I lose 18. Okay, so this is this, why I have a minus 8. So I have lost 18. Okay, so I have lost 18 what? 18 electrons, 18 nanocoulomb. Okay, good. Now you can say also how much charge was gained by sphere number 2. Okay, and you know how to do it. Okay, so let me go here and erase this. And again, the solution is given. Okay, so he has lost what? 18. Okay, 18 nanocoulomb has been lost. And 18 nanocoulomb has been lost means basically I have gained minus 18 nanocoulomb. losing this means basically you have gained this. Because I go from 22, I'm going to 4. You get my point, right? Good. Now let's solve this problem here, which is very important. So the problem reads, we have 4 points A, B, C, and D that are marked in a uniform electric field generated by oppositely charged plate as shown in this figure 7. Okay. So an electron, negatively charged, minus E, this is my electron, is transferred from its initial position A. So my initial position here is A. And it's transferred to my new final position B, C, and D. So B is final number 1, C is final number 2, D is final number 3. So I go from A to B. This is the first half. This is the second one. And this is the third one. Okay. So it's an electron minus E going from here to A, B, to B, C, and D. So question, rank the change in electrical potential energy. Read the question very carefully. Okay. Rank the change in electric potential energy of the electron at its new position. B, C, and D, most positive first. So first thing first, when you have a problem, you draw. We are in physics, okay? Always draw, and then you make sense of the problem. So here is positively charged, here is negatively charged. So we know that between them, you have an electric field going from higher potential to lower potential. Okay, so the electric field direction is this, and it's uniform between the plates. Now, second thing, what are the equipotential lines? Well, you know that the equipotential lines will be like this. They will be parallel to the plates. Okay. So this is an equipotential line, and this is another equipotential line. Okay. And of course, this will be higher potential, and this will be lower potential. Okay. Lower potential, because the electric field is pointing towards the lower potential. Okay, good. Now the question is, what is basically delta U? Okay. Delta U is U final minus U initial. So we know that delta U is Q delta V. You remember this formula. This is extremely important. Okay. Okay. Don't forget about this formula. Okay. Delta U, which is a change in electric potential energy. You remember that U is just QV. So that means delta U is just Q is constant, Q delta V. Okay? And we demonstrated this in class. It's extremely important. Okay. Now here, my delta U, my Q is negative. My Q is an electron. So minus E multiplied by delta V. Okay. Good. Now in path number 1, what's path number 1? I go from A to B. How is delta V? So delta V1, what do you think? Which is VB minus VA. V final minus V initial. What is the delta V? Is it positive or negative? It's positive, because VB is a higher potential than, VA. So this is positive. So that means that your delta U1 will be negative, because it's minus E multiplied by a positive number. So delta U1 is negative. 2, I go from A to C. What is my delta V? 2, which is basically VC minus VA. Of course, 0, because A and C are on the same equipotential line. So my delta U2 is 0. What about the third path? I go now from A to D. What is delta V3? Which is VD minus VA. It will be negative. Yeah, because VD is at a lower potential than VA. So my delta U3, which is minus E, multiplied by delta V3 is positive. So most positive will be 3, basically B. Then 0, which is C. Then the most negative will be, of course, B. Okay. Clear? Good. Conceptual question, good conceptual question. Okay. Solve the conceptual question. Solve all the recitation problem, as I told you. Now, second problem, which is quite similar, but another conceptual question. So you use your own, let's say, solution. Let's see here. We have an electron, again an electron. Okay. The charge of an electron Q is minus E. It's negatively charged, of course. Moves from point I, so this is point I, to point F. Okay, this is initial and this is final. In the direction of electric field. You see that the electric field is pointing in this direction here. So the direction of electric fields is always pointing towards lower potential. So VI is higher than V final here, which is V to F. Okay, I'm going into low potential. So if I put an electron here, which is negatively charged, of course, the electron wants to go in this direction because F of electrostatic force will be just QE, which is minus EE. The electron wants to accelerate to the left. But me, I'm applying a force here. So basically, I'm doing something to the electron. The electron is not an isolated system. There is me who is pushing the electron from this initial to this final state to overcome this electrostatic force, okay, to overcome the work of the electrostatic force. And the question is very simple. During this motion, how does the work of the electric field behave? I mean, is the work of the electric field positive or negative? And the potential energy, does it increase or decrease? Okay, so let's use work kinetic energy theorem or conservation of mechanical energy. Delta K plus delta U is equal to work applied. Now the work applied is not zero, because you see here, if I work applied was zero, the electron will go to the left side. So it will accelerate leftward. Okay, but here I'm bringing it rightward, so I'm applying a work here. Okay, so what do you think, delta K? Delta K is zero, of course. Why it's zero? Because we can assume that. Okay? It's an assumption, and it's a sensible assumption. Okay? It was at rest here. I hold it because of my work, and it's so I cannot use the fact that I can say, oh, delta K is zero. So work applied is just delta U. Now you remember delta U, which is the change in electric potential energy, is minus, this is minus the work of the electric force, or minus the work of the electric field. You see, because the electric force is a conservative force. Okay? So the work of the electric force is minus delta U, meaning delta U is minus the work of the electric force. Good. So let's do it now. Okay. So work applied. So work applied, as I said, is delta U, which is U final minus U initial, which is minus the work of the electric force. Okay. Good. So what do you think? The work that I have applied, is it positive or negative? Of course, the work that I apply is positive. Do you agree with that? Look at the displacement. The displacement is in this direction. And then I apply a force in the same direction. So the work that I apply, work applied, is positive. That means that the work done by the electric field is negative. You see, the work of the displacement is in this direction, and the work of the force, electric force, is in the opposite direction. So the work done by the electric force is negative. So that I know. So the work done by the electric force is negative. Okay? Good. Now, what about the potential energy of the electron field system? The potential energy, so of course, if work applied is positive, that means U final minus U initial, which is delta U, is positive, meaning U final is bigger than U initial. So it increases. So this is the right answer. Okay, you can check, all the rest are wrong. Okay, so we have this problem left. Let's solve this problem. So read it carefully. What do we have? So we have 2-point charge, Q1, which is here, and I give you Q1 minus 2 microcoulomb and Q2, which is plus 2 microcoulomb here. They are placed on the x-axis. This one is +1, Q1, Q2 is at -1 along the x-axis, as shown in the figure. So find the magnitude of the net work, of the work required to move a third particle Q3, and I give you Q3, along a straight line from point P to point R. So point P is here, so straight line towards point R. Okay, so this is the displacement here. Okay, so what is the work applied? That's what I'm looking for. There are many ways to solve this problem, but one way is to say that basically you use work kinetic energy theorem, or you use conservation of mechanical energy. Basically, delta K plus delta U is equal to work applied. Of course, delta K is 0 because I assume that they are at rest at the beginning. So this was my initial state. Okay, you have one here, and one here. So this is initial. And final, you have this one here, but now you have this one here. Okay. So, but still at rest. Okay, so delta K is 0. Now the work applied is just delta U. Now the question is to get delta U. What is delta U? You have two ways to get delta U. Here, delta U, the first way is very simple. Is to say that I'm moving charge number 3. So Q3 is here, Q1 is here, and Q2 is here. Okay, Q3 is here. So I'm moving Q3. So basically, work applied will be just Q3 multiplied by delta V. Now delta V will be what? Delta V will be, so this will give me Q3 multiplied by V final, which is VR, minus V initial, which is VP. You see my point? Okay. Meaning, I need to get what is the potential here created by Q1 and Q2 at this point R, and what's the potential here created by Q1 and Q2 at point P. Okay, so I'm moving Q3, so this is what I know. I'm moving Q3, so this delta U is Q delta V, because you remember we already discussed this before. So that's what I did here. Let's first calculate VP here. So I will have basically here what? Two opposite charge, Q1 and Q2 are equal in magnitude, opposite in direction. And at a point which is at equidistance, this point P, so is at square root of 2 meters from Q2, which is also at square root of 2 meters from Q1. So what does it mean? What is my VP? VP will be 0. You see, VP will be just K, Q1 divided by the distance, and the distance is square root of 2. Plus K, Q2 divided by the distance, which is square root of 2. Q1 plus Q2 is 0, so VP is 0. Okay, the potential here, so VP here is 0. Now what about VR? Well, VR here, I can calculate it. It will be K, Q1 divided by the distance. Now what's the distance between Q1 and R? It's just 1. Okay, plus K, Q2 divided by the distance. What's the distance between R and 2? It's just 3. So that's what I did here, Q. Okay. Now I put the numbers. Okay. So Q2 here is negative. So don't forget that. Okay. And I put it in, of course, in Coulomb. And Q2 is negative. Q1 is negative. Sorry, Q1 is negative. Q2 is positive. Yeah. So let's do it here. I have this is my formula. Now I have just VR, which is K, Q1, which is minus 2, 10 to the power minus 6 divided by 1. I know K plus Q2 is plus 2, 10 to the power minus 6 divided by the distance, which is 3. When you do that, you get VR is just minus 12,000 volt. Okay. Now you incorporate it here. So I know my work applied. So work applied would be just Q3. And what is Q3? Then 10 to the power minus 6 times VR. And VR I already calculated here, which is 12, minus 12, sorry, 10 to the power minus 10 to the power 3. So you calculate and then you get 12 millijoule. So this is a work applied. And we want the magnitude. That's why I said magnitude. Okay. Is it clear? Okay, good. Now, another way to solve the same problem is to do this, to say that basically we already discussed this, delta K plus delta U is equal to work applied. Because delta K is 0, so work applied will be just delta U. Now, delta U will be U final minus U initial. Now, what is U final? U final is this configuration, 1 here, and Q3 here. So what is U final? You count the number of pairs. It will be K, Q1, Q2 divided by the distance between Q1 and Q2. What's the distance between Q1 and Q2? Is 2 meters. Plus K, Q1, Q3 divided by the distance between them. The distance between them is 1. Plus K, Q2, Q3 divided by the distance between them. What is the distance between 3 and 2? It's 3. Okay. So you remember. So I have this particle, charge particle here, charge particle here, charge particle here. I count the number of pair and I calculate the total what? Electric potential energy. Now initial, what is initial? U initial, let me take another pen. So U initial is this, one is here, Q3, and one is here, Q1. Okay, now I can calculate what is U initial, number of pairs, and now the distance are different. So I will have K, Q1, Q2 divided by the same distance, which is 2, plus K, Q1, Q3. Now Q1, Q3 is this. Okay, the distance between them is just square root of 2. Plus K, now Q2, Q3 divided by the distance between them. Now the distance between them is square root of 2 as well. And then you calculate this difference. And when you calculate the difference, U final minus U initial, this just gives you work applied. And you will see, you will get the same answer, which is minus 12, 10 to the power minus 13 joule. Okay, and I want the absolute value, so you just take plus 12. Of course, if you take the difference of equation 1 minus equation 2, you will get what I want. This and this will simplify, and there are other things that will simplify, but I let you do it by yourself. Okay, now let's look at this problem here. And what do we have here? So read the problem carefully. We have an electron which is released from rest. At the origin, in a uniform electric field that points toward the positive x direction. It has magnitude. So I have a uniform electric field, let's say E. It is pointing toward the positive x direction. This is positive x, and E in magnitude is just 850 volt per meter or Newton per coulomb. So now I have an electron. So the electron is released from rest. So let's say it's released from here. This is my initial position. This is my electron, negatively charged, of course, is released from rest. So if I release the electron from rest, okay, so here work applied is 0, okay, because I release it. what will be the direction of the electron? Of course, the electron will be moving opposite to the electric field because the force is opposite to the electric field. So the electron will be moving in this direction. Okay. And let's say this is my final state. Okay. And the distance between the initial and final state is given 2.5 meters. Because the electric field is going in this direction. Okay. And the electron is moving in opposite direction. Now the question is very simple. What is delta U? What is the change in electric potential energy of the electron field system? You see, electric potential energy, as we said, is always between two interacting objects. But in general, we just say, what's the electric potential energy of the electron? But in reality, it's electron in the field, so electron field system. So how do we do that? Well, let's change color first. Let me choose a different. So what's the displacement? I start by initial here. This is my origin. This is 0, and I'm moving in the negative direction. So my displacement is this. Okay. Good. Okay. So now, what do? We want delta U. We know that delta K plus delta U is equal to work applied. Okay. By the way, here work applied is 0. I just release it. Yeah. So basically, delta U is just minus delta K. Okay. So if I know delta U, I can get delta K. But that's not the question. I just want delta U. Now, how do I get delta U? What do you think? So I can do it two ways if you want. Okay. The first way is delta U is Q delta V. Q is minus E. Do you agree with me? Now, what's delta V? Okay. So, of course, delta V will be equal to E times D. Do you agree with me? Okay. So, delta V will be V final minus V initial. By the way, this should be positive because V final is higher than V initial. That's why my electric field is pointing in this direction. Okay. And this is just ED. And I can calculate that. So I have minus E times the electric field times the distance. I put the numbers minus 1.6 10 to the power minus 19. Everything in SI units. Electric field SI units, Newton per Coulomb, here Coulomb, and then I multiply by a distance. So the distance is 2.5. And you get minus 3.4 10 to the power minus 16 joule. And this is one way. Another way to do it is we know that delta U will be minus the work of the electric force, minus the work of the electric field. So this will be minus. Now, what's the work of the electric field? The work of the electric field will be integral of F dr or ds if you want. Okay. Okay. Now, but the electric field is constant. The work of the force is constant. Okay. So I can just say minus F, which is the work of the electric force multiplied by the displacement. Now, what's the displacement? The displacement is D vector. And you know here that the electric force is pointing in the same direction as the displacement. This is F. Electric, of course, the displacement is pointing in the same direction. So this is just minus F D but you remember in magnitude. So minus, what is F? F is E multiplied by magnitude of E, and B is V. And this is delta U, which is just minus the work of the electric force. And you see that it gives you the same answer as here. Okay, good. Next question. Well, this one is also straightforward, but let's solve it. Let's read it first. We have a particle which has this charge, and it's fixed at point D. So the particle Q is fixed at point D. Then I have another particle that has this mass, and the charge is capital Q, 5 nanocoulombs. It starts from rest at point B and moves in a straight line to the right. So it starts here and move to the right, B. And now the question is, what is the VQ at B? So how do you do? I can use conservation of mechanical energy. Delta K plus delta U is equal to work applied. Now what's delta K? Of course, it will be delta K of this particle at rest, which is 0, because basically this particle is fixed. It does not have any delta K, 0. Now plus delta K of the particle B. Of course, the particle B will have a final kinetic energy, half m. It has a mass VB squared, its initial kinetic energy is 0 as well. Okay. This is delta K, change in kinetic energy for this and this. Now what is delta U? Delta U, I can calculate it two ways. I can say that it will be U final minus U initial. Okay, what is U final? U final is when Q is here. Okay, this is final. So what is U final? It will be K, Q divided by the distance between them. The distance between them will be 10 centimeters, so 0.1. What is U initial? U initial is this. This is the initial distance. Okay, so this guy is here, this guy is here. So what is U initial? It will be K, Q, capital Q divided by the distance between them, which is 0.05. So basically, U final minus U initial will be just K, Q, 1 divided by this 0.1 minus 1 divided by 0.05. And this should be equal to work applied. What is work applied is 0. Okay. Because it's an isolated system. 2 positive charge, 1 here, 1 here. This one is fixed. And this one is released. You know, they repel each other. I'm not doing anything. Okay? I did not apply it. An external agent is not applying the work. The work applied is 0. So that's it. I know everything. My only unknown is VB. I know the mass. I know K. I know Q. I know Q. I know these distances. I just put it on the other side of the equation and then I solve. When I do that, I get VB, V final, V of Q at B, which is V final, is 0.085 meters per second. Okay. Good. So you see here, what I did is I'm using basically U, which is K, Q divided by the distance between them, between Q and Q. And I do it for initial and final. But the other way is to say that, well, delta U is just capital Q multiplied by delta V, because capital Q is moving. Now, delta V will be basically V final created by small q minus V initial created by small q. Okay? And it will give you the same answer, by the way. Okay, okay, good. So Let's go to the last problem that I want to solve today. Please, for the quiz and the final exam, solve all the recitation. Okay. This recording will be posted on Blackboard. You have time, and we have a quiz on this chapter next week. And it will be on Tuesday, okay? And of course, as usual, it will come from out of the recitation problems. One multiple choice question and one regular quiz question, as I already announced. Only those who will watch the video will get this extra information. And go for the rest, okay? You have many other problems. Solve as much as you can, and most importantly, understand what you are solving, okay? Critical thinking. Now, let's look at this problem. We have a very, 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 very large sheet, which is made of an insulator. So it's an insulating sheet. It has a uniform charge density of 3.52 nanocoulomb per meter square. Let's draw. So this is my very large sheet. It's insulating. Insulating sheet. So I know sigma, which is the uniform charge density. So what is the electric field created by an insulating sheet? If it's an insulating sheet, electric field is just sigma divided by 2 epsilon naught. If it was a metallic sheet, it would be sigma divided by epsilon naught. You remember that? Okay, so it's an insulating sheet, sigma divided by 2 epsilon naught. So that means we can calculate the electric field. What's the electric field? The sigma. Sigma is 3.52 nanocoulomb, so 10 to the power minus 9 nanocoulomb per meter square divided by 2 times epsilon naught, which is 8.85, 10 to the power minus 12. So if you calculate this, what do you get? Minus 12, okay? Epsilon naught minus 12 here. So what do you get? You use your calculator. And you get your electric field. Now, once you get the electric field, here I'm asking you what? I'm asking you for this electric field, for the electric potential produced by this sheet, what is the minimum distance between 2 points that differs by electric potential of 210 volt? So basically, I can know what's the electric field. Okay. Now you know that V final minus V initial will be just minus integral between initial and final. Be aware of this order. Okay, final minus initial, final of E dot ds. Okay. Now, of course, if E is constant, like outside this sheet, I can get it out. I will have minus E dot the displacement. Now the displacement, let me call it D. Okay, good. Now, what is this? You can get this because here what I will do is I will be looking at, you see the electric field is always pointing from high potential to low potential. Okay, so let's say the electric field is pointing away. Let's say, here it's positively charged sheet is pointing away. Okay. Now, the displacement, what do you think? So here I'll be choosing a displacement which is also going. Always I'll be choosing that. Okay. I'll go from a displacement which is going from, so D, the vector is from initial to final vector. Okay, and I will always choose it to go from low potential to high potential. Okay, so the displacement I will be choosing it this way, from low potential to high potential. So here, if I do this, you have 90 degree, you have 180 degree between them. So this is E pointing away, but the displacement that I'll choose will be from low potential to high potential. Okay, let me write it down. From low potential to high potential. So basically this will just give me minus E B cosine 180 degree. So this just give me plus ED. This is V final minus V initial and delta V. And I know this, by the way, this is just 210. So that means distance I'm looking for will be what? Will be 210 divided by the electric field that I found here, which is just sigma divided by 2 epsilon naught. And if you do that, you get a distance of 1.6 meters. Okay. Good. Okay. So that's it for today. Please solve the rest and solve as much as you can. And I wish you the best for what's coming, inshallah. Assalamu alaikum.